Hey everybody, thanks for tuning into the final video for Unit 4 on Earth Systems and Resources. Today we're going to talk about solar radiation and the causes of Earth seasons, global climate patterns and the difference between weather and climate, and lastly El Niño Southern Oscillation, and look at the differences between El Niño and La Niña, determine exactly what those are. So let's start with the Earth seasons. What causes the Earth seasons? It's not the Earth's distance from the Sun, it's actually the tilt of the Earth's axis. The Earth is on an axis that tilts about 23 degrees, right? So it's not straight up and down, it's tilted a little bit. And that's going to affect the way that the sunlight hits the Earth. It's going to hit the Earth at an angle. So the angle at which the sun is hitting the Earth is going to determine the intensity of sun in that area. We've talked about this already, right? In an area that is perpendicular to the sun's rays, it's going to get the most direct sunlight spread out over the smallest area. But in an area that is closer to the poles, right, the sun is coming in at an angle, so the same amount of sunlight is getting spread over a larger area, and so it's decreasing the intensity of sunlight in that area. So we see the most intense sunlight at the equator, and it decreases as we move towards the poles. This is what causes the Earth's seasons. The Earth's seasons are not caused by how far away the Earth is from the sun, because believe it or not, the Earth is actually closer to the sun during the northern hemisphere winter. It's got everything to do with the tilt, however. So we're going to be talking about the northern hemisphere because that's where we live in the United States, but everything in the southern hemisphere is opposite for us. So their winter is in our summer and vice versa. Their spring is our fall, right? So they're celebrating their winter time in June, July, August, etc. So in summer in the northern hemisphere, the Earth is tilted towards the sun. Or at least the northern hemisphere, I should say, is tilted towards the sun, which means that the angle of the sunlight is less perpendicular to where we are in the northern hemisphere, less at an angle and more perpendicular. It's more of a direct level of sunlight. So the solar radiation is more intense during the summer. And as you might know, the days are longer. The sun rises earlier and sets later, stays in the sky longer, and the sunlight is the most intense. That's when we get the most heat energy, and that sunlight is not hitting as much of an angle because we're tilted towards the sun. In the wintertime, though, that flips. In the wintertime, we're tilted away from the sun. The sun's over here now on the right, and it's hitting the northern hemisphere on a pretty severe angle and the southern hemisphere on a very minimal angle, which means it's going to be summer down there and winter up north. So in winter, obviously, we're getting much less solar radiation. The sun rises later, it sets earlier, so the days are shorter, there's much less solar radiation, and it is much less intense. If you look at this diagram, it shows all the pieces, right? So in the wintertime, the northern hemisphere is tilted away from the sun, and as the Earth travels around the sun, right, this tilt stays the same direction, right, at the 23.5 degrees. So as we move towards summer, suddenly the northern hemisphere is tilted towards the sun, so those rays are coming in at a more direct angle. Meanwhile, in the southern hemisphere, it's tilted away from the sun. The rays are hitting at a more indirect angle. And you can see the amount of the northern hemisphere that is lit up here is much higher compared to the amount of the southern hemisphere, and vice versa here. The southern hemisphere is much less darkness than the northern hemisphere, and that also reflects the length of days in each respective season. Here's another diagram showing the same thing with sort of the angle of the sunlight, right? Again, in the wintertime, the most direct sunlight is hitting the southern hemisphere, or at least in our wintertime. That's their summer, but during our summertime, the most direct sunlight is hitting the northern hemisphere. Okay, part two. Let's talk now a little bit about the difference between climate and weather, because climate and weather are driven by the sun's energy and change with the seasons, but there's a difference between the two, and it's a really important distinction, especially when we're talking about things like climate change, because you might often hear people say something like, oh wow, it's 50 degrees in February, so much for global warming, but that's not actually the case, right, because what they're talking about is weather, and climate change is all about climate. Weather, generally speaking, is short-term on the span of days to weeks to months. Climate is much longer-term on the span of decades to thousands of years. Climate and weather are not the same thing. Climate are long-term geological patterns of an area, of their atmospheric conditions. Weather is very short-term and quickly can change. right? Weather or climate is what we expect to get. Think about like, what we expect to see in a biome, but weather is what we actually get, right? Weather can change very rapidly, whereas climate is you're looking at things over a much wider time span. Like I said, weather is short-term atmospheric conditions over the course of hours or days. It can include things like temperature, humidity, pressure, amount of sunshine, not sunshine, amount of precipitation, the type of precipitation, how much clouds, how fast the wind is, what direction it's flowing, etc. This is the stuff that impacts us on the day-to-day that we're thinking about. Climate, on the other hand, is general patterns of atmospheric conditions over very, very long periods of time, right? We're talking tens of thousands of years, and you can look at geological changes in climate over the spans of thousands to millions of years, but you can't really do it on the span of days. So when we talk about climate change, we're not talking about stuff we're seeing on the day-to-day or really even year-to-year, but more like decade-to-decade. So what determines the patterns of climate that we see, right? What determines where biomes are found? A lot of that has to do with the availability of the sun and the angle that it's hitting at, right? I was just talking about earlier, the angle of the sun that's hitting the Earth and the tilt of the Earth's axis is going to change the season we're in. We've also talked about global air circulation, like Hadley cells, and how that can affect the climate patterns, and ocean currents, such as the Gulf Stream, which can affect climate patterns. But something else we haven't really talked about are topographic features, which I will get to in a second. I do want to make it abundantly clear that all weather and climate on Earth, clouds, rain, etc., is all driven by the sun's energy, evaporation, precipitation, all that stuff. So keep that in mind, that all of these processes, hurricanes, cyclones, tornadoes, all of that originates from the sun's energy. And you could see changes in Earth's climate, right, around the globe. Generally speaking, it's hotter towards the equator, more tropical climates, and as you move towards the poles, it becomes, well, more polar, more cold, and that's going to line up with the patterns we see here, generally speaking, with the angles of the sun's rays. The ocean currents and global air circulation will distribute that heat in different ways around the world, and topographic features like mountain ranges and proximity to water. Oh, I made this a little too big. Mountain ranges and proximity to water can change climate and weather on smaller, more geographic scales. And one of the greatest examples of that is something called a rain shadow. A rain shadow is basically that this idea that mountains will prevent rain clouds from traveling over them, right? So mountains are oftentimes located next to bodies of water, and that water will evaporate. It will get carried by winds up towards the mountains, but they don't rise high enough to make it over the mountain, because as that hot air rises, carrying hot water vapor, it condenses and it cools and it condenses and it falls as precipitation, usually on one side of the mountain, doesn't get to make it over to the other side, can't rise high enough. And so on the other side of the mountain, we tend to see things be a lot drier. Great example of this is the Rocky Mountains. California is quite dry, but compared to like New Mexico, Arizona, Nevada, etc., on the other side of the Rockies, California actually has quite a large amount of precipitation. You can see this in Hawaii. Really fantastic example of a rain shadow. We're looking from above. This is a mountain range here, and you can see clouds and that are from evaporation from the ocean are getting blown towards the mountain. They're getting blocked by the mountain. They're dropping all their precipitation here. We're seeing a lot of greenery and vegetation and productivity here, and on the other side, nothing. That's a rain shadow. So it's not just about the Earth's tilt, it can also, or the wind patterns, but it can also be some topographic features like mountains as well. Okay, and the last topic I want to talk about is El Niño Southern Oscillation, also known as ENSO. You may have heard of El Niño before. And it's basically a recurring climate pattern that happens in the Pacific Ocean on the equatorial current, right on the equator here in between the United States and South America and Australia, Indonesia, and Southeast Asia. And normally there are normal conditions, and then it will enter an El Niño phase, and then after that it will enter a La Niña phase, and then it will go back to normal. And it cycles irregularly, pretty irregularly. Could be 2 years, could be 7 years, while that's unpredictable, we can actually are able to predict the impacts of the different phases. So El Niño and La Niña have impacts on the temperature, the precipitation, the winds, ocean circulation, etc. That is all very predictable and easy to track. So normally what's happening in between the Americas and East Asia and Australia is that there's a equatorial current that is carrying this water away from, in a westerly direction, so away from North and South America and Central America and towards Australia and Asia. And what this is doing is it's going to cause all of the warm water to sort of pile up over here, and it will result in cool water being pulled from deep below the ocean. So things tend to be cooler and drier over here, and things tend to be hotter and wetter over here during normal conditions. Right, and if you're wondering, well, why are these winds the way they are, think back to when we talked about Hadley cells. Right, the Hadley cells, we have winds traveling towards the equator from 30 degrees north. Those are getting deflected by the Coriolis effect, so they're moving south-west. Right, these are those northeast and southeast trade winds that are coming from the northeast, coming from the southeast. This is what's driving these currents here, those trade winds. But what happens during El Nino is that these trade winds get disrupted by the westerly winds coming from the west that disrupt things, right? So instead of the current moving from the east to the west, it's moving from the west to the east. And so the trade winds are weakened, and we see a reversal in that pattern. So warm water starts to pile up over here. We start to see more rain, and things start to dry out here, and there's cooler water. I'll show you a few more diagrams, and I'll show you a demo in class so you can really get a good hold on what's going on here. And then finally, as El Nino is occurring, right, with the westerly winds blowing things to across the Pacific towards South America and Peru, away from Australia. In La Niña, we see a return to normal conditions. It's kind of like normal conditions all jacked up. So like this, maybe times 2 or 10 or whatever. So we see a really strong westerly current and more extreme conditions compared to the normal conditions. So here's a map that shows the differences between El Nino and La Niña. So we've got Australia, Asia, South America, North America. And during El Nino, we see that water is being, the normally easterly blowing trade winds are disrupted. They're now blowing west, so warm water is sort of in the North and South American areas. And we see a lot of warmer and wetter air here, whereas on the Indonesia, Philippines, southern Japan, etc., we see cooler than average temperatures and less rainfall. Versus La Niña, we see the opposite. It's cooler and drier over here, and it's warmer and wetter over here. And El Nino will also have a big impact on something called upwelling. And upwelling is this idea that as wind blows away from, or as wind blows across a body of water, and it blows away from the land, the wind is going to sort of catch the surface water and pull it along with it. Right? If you imagine yourself blowing over a cup of water, you're going to push that water forward. And as that water moves forward, water molecules stick to each other through a property called cohesion. And so as that water moves this way, it's going to pull water from beneath upwards. And water from very, very deep is going to get brought upwards as well. That's something called upwelling. And upwelling is going to be something that happens a lot depending on, or in different areas, depending on whether we're in El Nino or La Niña. Upwelling will bring cold water to the surface because water is colder deeper down because it's more dense down there. Cold water is denser, so it sinks, but also the sun doesn't reach there to warm the water. But also, at the bottom of the ocean, if an organism dies, it doesn't just float there and decompose on the surface. It sinks to the bottom where things like crabs, lobsters, and starfish will start to break it down. Decomposers are on the ocean floor just like they're on the terrestrial floor. And so the ocean floor is absolutely loaded with nutrients. Nitrogen, phosphorus, calcium, potassium, carbon, you name it. And so when upwelling occurs, it's actually going to bring all those nutrients to the surface. Right? So as the wind blows away from the shore, it will pull the surface water away, pull up that deeper, colder water that is also loaded with nutrients. And so suddenly, this coastal area, this in the photic zone or the perhaps the limnetic zone, right? These areas near the surface suddenly have a huge influx of nutrients. So phytoplankton are going to start booming, right? We're going to see an increase in algae and primary productivity. Zooplankton and other things that eat the phytoplankton, their population is going to go up. The fish population is going to go up. The seabird population is going to go up because there's more nutrients, which means there's more algae, which means there's more food for zooplankton, which means there's more food for fish, which means there's more food for birds. So upwelling can have a really massive impact on the aquatic populations here, and ultimately on the economy as well, because more fish means more fishing and even more tourism. So if we look at these El Nino and La Nina conditions, we see that normally with those westerly blowing trade winds, the northeast trade winds blowing from east to west, they're blowing away from North and South America, pulling up cold water from the deep, which is why it's colder, and obviously, and they're also pulling up those nutrient-rich waters. So during normal conditions, we see great fishing grounds and high primary productivity in these waters. Upwelling North and South American Pacific coast leads to a nutrient boost in this area. Meanwhile, when El Nino occurs, we see a reversal. Now the winds are blowing from west to east, and we don't see that upwelling anymore. There's not even really any upwelling over here, although there could be. We might even see downwelling, which is just the opposite of upwelling, where water is pushed against the shore, has nowhere to go, so it goes down. What that might do actually is deliver dissolved oxygen down to deeper depths, but it's not going to have any impact on nutrients, so it can actually result in a significant lack of nutrients, a crashing of the phytoplankton population, and loss of fishing communities as well. So El Nino can be really bad for the fishing industry. And then during La Nina, we see a little bit more intense version of normal conditions. I'm going to flip back to normal real quick. Pay attention to the upwelling. You could see during normal conditions, it's not quite as severe as it is during La Nina. But we see, again, those westerly blowing winds, those northeast trade winds blowing to the west, causing upwelling. So again, we'll see a nutrient boost during La Nina. La Nina is currently going on as I record this video. It is on November 12th, 2020, there we are currently in a La Nina phase, and we can tell by, as I've highlighted here, below average sea surface temperatures extending from the dateline to the western or eastern Pacific Ocean, which is this map here. So Mexico, South America, Australia, Indonesia, etc. You can see that we've got the cold water piling up here, colder than usual. A sea surface temperature anomaly is meaning, well, compared to the average, is it colder or warmer than usual? So 0 means, well, it's as average, but a red means it's hotter than usual, and blue means it's colder than usual. So these waters are colder than usual, and these waters over here are hotter than usual. That's significant of a La Nina. And ENSO, whether it's El Nino or La Nina, can have massive impacts on hurricanes, cyclones. They can change downwelling and upwelling, like I mentioned, and they can have impacts on weather patterns. Right now, we're going to be into a La Nina winter, is what we're about to enter. So us in New England might actually have a warmer winter because of that. In southern United States, things will be drier. Northern United States and Canada, things will be colder, and the Pacific Northwest will be very wet. We see different patterns if it's an El Nino winter. And globally, La Nina can have some massive impacts as well. So does El Nino, but I just have a map for La Nina right here because that's what we're in right now. So we'll see that things are, I just kind of talked about North America, but we see things that are hotter and wetter over here in Oceania. Things tend to be cool and wet in Japan, right? It's got global impacts stretching all across the globe. So don't think that it's just happening in this little strip here or just in the United States. Okay, that's all I got for you today. I will do a demo in class looking at El Nino and La Nina, which will hopefully help explain some of what's going on, and we'll follow up with an activity. If you've got questions, bring them to class, and I will see you next time.